So we finished Riemann-Roch theorem with one glitch. This y is x omega differential. It's canonical. The associated maximal divisor y is it equal to that of omega plus principal divisor of x. So for this I have to go back, and I have corrected that in the notes which I'll upload. So when we define differentials here, when we define this x omega, right? So what does x omega do? It instead of applying omega on r, now you will apply omega on r times x. R is the adel. So previously, if omega would kill r, then now x omega will kill r by x. So because 1 by x is also a function, so we can look at r by x. So if you remember this equivalence, from this actually everything else will follow. So omega is given in big omega d, which means r plus d is greater than or equal to 0. So where does r by x live? So r by x actually lives in d plus x. That is the last property. X omega lives in big omega d plus x. So the proof is what I just said, that if omega annihilates ad plus k, then x omega actually annihilates 1 over x times ad plus k. And so since adel r plus d is greater than or equal to 0, r by x plus d plus x is also greater than or equal to 0. It's equivalent. So you go from big omega d to big omega d plus x. So it's actually a plus. That was the mistake. And yeah, rest is fine. This also I have completed the proof. So why is this? Because we'll also use it, need it in Riemann-Roch. When you send a x function x to x omega, why does d plus e become minus e? So again, you recall that omega r equal to 0 if and only if x omega r by x is equal to 0. And here the x that you are given is x plus d plus e will be greater than or equal to 0, and small omega annihilates ad. So you take any r such that r plus d, adel r plus d greater than or equal to 0. So for r by x you will get principal divisor x plus d greater than or equal to 0, from which you use the property that x plus d plus e is greater than or equal to 0. So you get that r by x minus e is also greater than or equal to 0. So r by x actually lives in minus e, big omega minus e. That's where now x omega will live. I mean r by x lives in a minus e, the adel, and so x omega annihilates that. So this is just to show that everything is consistent, and that's what is used in Riemann-Roch. So ultimately Riemann-Roch will, so here also correction was that small omega is in big omega associated, maximal associated divisor of omega, bracket omega. So x omega will be in this, and it's an if and only if. So this is omega plus x, not minus. Yeah, that's if and only if, and from this you will get the identity that x omega is equal to omega plus x. And Riemann-Roch is just now one line proof. You just look at the map which sends y from L w minus d to big omega d by multiplying by omega, and then everything works. You can show that this phi is an isomorphism. Okay, so yeah, that finishes Riemann-Roch and corollaries. And in Jacobian variety, So let's recall that. So Jacobian variety will be given by these, we are essentially partitioning divisor 0 classes into these into these subsets which we call C gamma. But how does it come about? So you basically go over those degree 0 divisors D such that L of D plus something which is fixed for now, this dimension should be equal to 1. Yesterday I said 2, but 1 is also fine. So basically the L sheaf should not be empty, that's all. As long as something is there, even constant is fine. You pick that D and put it in D gamma, and you do this for all possible fixings of this thing, 2g minus 1 infinity minus D gamma. So you will basically partition your degree 0 divisors into these D gamma chunks. They'll be clustered, and that the advantage of this L of this D prime equal to 1 is that you can actually now write down D prime as a sum of points. It's a positive divisor, and so two things, it's a positive divisor and its degree is G, so it's a sum of G points. That is what the property of this D is, that corresponding D prime is sum of points, and you just take those sum of points now minus G infinity and call that C gamma. Okay, so you have these C gamma are the clusters, and these clusters, the way we have defined them, it's actually a variety. It is potentially a high dimension variety, and again the way we have defined them, actually you can look at the union, that will also be a variety. You can glue them, and that variety covers everything in class degree 0 class group, and seen as a variety we call it the Jacobian variety, but as a set is the same. So that is the Jacobian variety. Now it's a very special object. It's the most famous object in math because it's a variety. It's coming from a system of equations, polynomial equations, but the points you can actually add them and you get another point, which basically, these things only happen in vector spaces, but this is not a vector space, it's a variety here, but it has this, it affords addition, and it has actually many other things which I will point out, but let us first see the elliptic curve case again. So G equal to 1, genus 1 is the elliptic curve case. So in that case, actually the Jacobian, we will show that it's the curve itself, and we'll see how the addition happens. So basically, the way we have defined C gammas, we are only looking at a point minus infinity. That is an element in JC. So if you want to add 2 points, what will happen? 2 elements, so P1 minus infinity has to add it to P2 minus infinity. And the claim is that this should be equal to a third element, which again has to look like P3 minus infinity. So what should that be? So for this, actually I have to now define what is minus of P3 minus infinity. So that I should do next to make this clearer. But once I show you what is the negative of P3 minus infinity, let me call that for now P3 prime minus infinity. See, because before doing addition, you should at least know how to negate an element. So what is the negative of P3 minus infinity? So let's call that to be P3 prime minus infinity. So then you have to satisfy this equation. P1 plus P2 plus P3 prime minus 3 infinity should be equal to some function, principal divisor of a function. And P3 prime minus infinity should be equal to negative of P3 minus infinity. So this sum should also be a function, right? So you have to come up with two functions. So as you already know, how this is done is, so I have drawn a better elliptic curve now. So here you see that the elliptic curve, which is the, so you have the x-axis, y-axis, origin, and the red curve together is the elliptic curve. So it should intersect x-axis in 3 points, because it is like y square equal to x cube plus x. So x cube plus x has 3 roots. Those are the 3 intersection with x-axis. P1, you take P1, you take P2, and P3 prime. What is the function? The line that passes through them, right? That's L. And what should P3 prime be? P3 prime and P3 and minus 2 infinity. So infinity should be a pole of multiplicity 2, and P3 and P3 prime should be the zeros. So this is the line L prime, and we generally draw it vertical parallel to y-axis, because the point at infinity is like vertically upwards. Y equal to infinity is basically the point at infinity. So the vertical line will give you the opposite of P3 minus infinity. So that's P3 prime minus infinity, and that has to be in line with P1 and P2. Okay, so this is the algorithm to do addition and inverse on an elliptic curve. Okay, so you get this from the way we have defined the Jacobian variety, actually, which happens to be the elliptic curve in this case. It doesn't grow. So what you learn is that this when genus is 1, the J of C is same as C, which is the same as degree 0 class group, which is the same as points minus infinity. So these points minus infinity, these are the distinct elements in JC and in CL0. Why are they distinct? You just show that for different points P and Q on the curve, elliptic curve, P minus infinity and Q minus infinity are not the same modulo the principal divisors, which again follows from the picture, because why does it follow? So if you take, let's say you take P1 and P2, so what you have to, or you can look at the above, actually it will be same as the above equation. So let's say P3 prime and P3 are this has to be written separately. Basically, if they are, then what will happen is you have to have this then. If these two are same, then essentially P minus Q has to be equal to a principal divisor of a function. Functions on the elliptic curve are just lines. They are linear functions. So you have to come up with a linear function G which has P as pole 0, Q as pole. That is impossible, because every line on the elliptic curve gives you 3 solutions minimum, and then the point at infinity also, you get 4 solutions minimum, right? So for different points you can't have equivalence. So all these different points give you P minus infinity different elements in the degree 0 class group. So you have completely classified degree 0 class group. You can also classify the canonical divisor W. because remember that canonical divisor degree is 2g minus 2, which is 0. So then the only element is then it is in CL0, and in CL0 the only thing that works is infinity minus infinity, so that's 0. So canonical divisor in the case of elliptic curve is actually just 0, which means that Riemann-Roch has this form. So omega d is equal to L of minus d, right, which again you can calculate. So for d equal to 0, these are just constants. For positive d, it's empty, and for all other cases, it will be something non-trivial, right? So omega d for all divisors is quite explicit because it's just L of the negative. Yeah, so this tells you almost everything you want to know about elliptic curve in a field independent way. You don't need information of the field in these proofs.
No, what were you thinking about the diagram? You asked a question that follows from.
Sorry?
Whether it follows from the diagram or not.
Well, in the diagram, when you draw a line, you have to have 3 points that you see, and one possibly at the infinity. Not possibly, one at the infinity.
No, there will be 3 points which will be zeros of that line.
Yes.
And there will be 3 poles at infinity, right?
Correct. Yeah, the infinity part will just balance.
Just balance the zeros.
Yeah. So
From that we
so just having two things in the union of zeros and poles is not possible. It can be done, I think. I don't think you can do it just by looking. You have to first realize that g is a linear function and then substitute the linear function. So for example, y is equal to mx plus c. You just substitute it in the elliptic curve equation, so it will become a univariate. Now the univariate over algebraically closed field has 3 solutions, and from there you can see. So all those solutions, then they have to be P. But then if all of them are P, then they are high multiplicity. And there you are saying that multiplicity of P is 1. So you always get some contradiction. Yeah, so I hope this Jacobian variety part is clear. Especially looking at the elliptic curve, you can imagine how it will behave for higher genus. Higher genus, the problem is that you will not be drawing lines, you will be drawing non-linear objects, because G will be, for example, G can be quadratic. So then you are actually, through the points, you are drawing a quadratic curve. So it's not easy to analyze it either pictorially or algebraically, but this picture can be used as a guide. So yeah, the Jacobian variety is, as I said, like the most important object in math. So it is basically a junction of many areas of math. So what are those areas? So it obviously is now a smooth projective variety of high dimension, right? So it's a geometric object. It has geometry. And it's not a curve, it's actually a high dimension variety. By the way, this it will not be an affine variety because I said gluing. So whenever you want to glue, you should think of these affine patches. So you glue and then you actually get a projective variety. So this is another reason why we'll prefer projective over affine, because in these more general situations you actually want to glue things. So affine, when you glue affine, you will not get affine, you will get something else. So that's this is where projective varieties are more fundamental. So it has geometry from there. It is now also a group. So it has group structure. And this group structure is not arbitrary. It's actually is an abelian group, and it also has an automorphism coming from the Galois group of finite fields. So the Galois group of the finite field, which you saw in assignment 1, this actually acts on it. Right. So the first thing gives you the abelian group structure. So you can use, you can try to use abelian group structure theorems like product of cycles, etc. And the second thing, because Galois group is acting, you can develop more complicated theories. For example, Galois cohomology theory is one way to study this, but that we will not do in this course. So each of these points, bullets, actually lead to many areas of math. Then it knows the topology of the curve. Right, so this was one of the main motivation to define it, because we wanted to compute the topological invariant of a curve. So, so it clearly has topological motivation, and also it's the class group. Of transcendence degree 1 function fields. Right, so this was the other thing we showed, that it's also equal to CL0 of a curve which is basically function field transcendence degree 1. So it is class group, it is topological, which is the Zariski topology basically, but also classical topology is embedded in it. You can, when you are over complex field, the classical topological things can also be recovered like this. Although proofs will be very different. We are not doing those proofs in this course. There is whole group theory, representation theory, cohomology theory here, and of course algebraic geometry is here. So needless to say, all great mathematicians have dabbled with this, because it covers so many areas of math. So what we will do next is just study one, which is the primary aspect of JC or CL0C, which is the Frobenius action on it and counting points. So take the field to be finite field. In fact, take the base field of constants to be just prime field. So in that case, you have a special map, which is the Frobenius map. So what does Frobenius map do? It sends a point to this point. Right? That will be the definition of Frobenius in this course. So there is this special map Frobenius, which by the way is also the source of Galois group action of FP bar. You are basically applying this map, so it's an automorphism on the class group, because the key thing is that a point goes to another point. So this is then acting on JC or the class CL0 as a linear map. Right, because clearly if you have a point P1 and a point P2, then the Frobenius on P1 plus P2 will just be the same as Frobenius on P1 plus Frobenius on P2. That's again coming from the way we had defined addition in the divisor group. So it is almost by definition a linear map. Well, by linear we mean Z linear actually. This is over integers right now. It's a Z linear map. So you can ask about its characteristic polynomial. Right? So you have a map and you have a vector space. So the first thing you should ask is what is the characteristic polynomial of this action? Of Frobenius on JC. Okay, so this will be the guiding principle of what the next the chapter that we will start next, which is that study of zeta function of the curve. So the zeta function ultimately will turn out to be the characteristic polynomial of this action. Okay, so the rest of the course will be devoted to just that study and proving the Riemann hypothesis for it. So the zeta function of this curve, or which is same as transcendence degree 1 function field. But in computation we are more interested in counting points on curves, so that will turn out to be equivalent as well. Yeah, curve is just a geometric object. The actual object is the function field. Whenever we write C, and especially div C, it's very hard to make sense of it geometrically because the points P1, P2 are not actually points. As I said, it's a cloud of points. When you take your field of constants to be just FP, your P1, P2 is actually prime ideals. So div C is just the sum of, formal sum of prime ideals. You are not actually adding ideals, it's just a formal sum. But when you go to K bar, then they actually become points. So when inherently it's actually an algebraic definition. If you want to think of it independent of the field. Okay, so yeah, so I don't think I defined this before. So what is the zeta function of a curve? Let's do that today. So we'll assume now the field of constants to be FQ for some prime power Q. P is a prime. So it's a finite field, and so C is a smooth projective curve. Which has coefficients from that base field. Okay, so this is what we mean by over small k. The coefficients come from this base field. Also this C is isomorphic to the, I mean, it is just modeling this abstract curve of its function field. So in other words, if you were given in the input a curve which is not smooth, which has singularity, so you will go to its function field, and then from the function field big K you will come to a curve which is smooth projective, and this study will only be for that. Okay, it will not study the singular points. It will only study the function field of your given curves model, which is smooth projective. So it's inherently a study of the function field, not the curve itself. So, but of course, our computational interest is in point counting on the curve. That is for n, how well can we estimate the number of points, which can I can also write like this. Which is number of FQN points on the curve. Okay, so FQN points means if you had this, if it was a planar curve given by f of x comma y equal to 0, then x and y you are only allowed from this field. Okay, so for example, n equal to 1, what is n1? N1 is just what are the x comma y pairs which are on the curve where both x and y is constant in the base field. Okay, this is not a simple thing, because when you are given, even if you are given y square equal to x cube, this I think example we saw the beginning of the course. Even in the case of y square equal to x cube, you don't really know, maybe that it's too simple, but y square equal to x cube plus x. So definitely for y square equal to x cube plus x, you don't really know for what x you will get a y, right? Because when you fix x, you have x cube plus x, but when is it a square? In the base field FQ. So sometimes you have a square, sometimes you don't, and so you have to divide the computation into two parts. Both the things are unpredictable. It's almost a random event. So this N1, even N1 is actually a very hard thing. There is a lot of randomness in it, even in the case of elliptic curve. So, but it's a well-defined question. Can you actually compute N1? Right? That is what we are interested in. This question appears a lot in computer science and in applications. So Nn is the same as number of points in the curve such that the degree of the point divides n. Is this believable, or should I prove it? So for example, when you take n to be 1, right, then you say that you are basically asking for degree of p to be 1. which is saying that they'll all lie in FQ. When you take n equal to 2, so n2 is basically, big N2 is, you are saying that the degree of the point should either be 1 or 2, which is saying that either it's in the base field FQ or FQ square, right? Because degree is given by, so you have to recall what is degree of a point. Degree of a point is the least field, smallest field where your point lives. So you are actually asking for all the points in that field and its subfields and so on. So P essentially lives in this finite field. Yeah, this will be hard to write. Let me use Galois field notation. So Galois field Q to the dp. Okay, so this will be contained in Galois field Q to the n if and only if dp divides n. That's all. So by definition, a point on the curve lives in the finite field of size q to the dp, and if your point also happens to live in q to the n, then it basically means that it's equivalent to saying that degree is a factor of n. This is by the property of the way finite fields are. Lattice of the finite field gives you this. So so you get this condition. Yes, so we will study its generating function, let's say. So what is n1, n2 dot dot is a series of numbers. Its generating function is sigma nn t to the n, seen as a power series. So are you aware of this notation, z double bracket t square bracket? So this basically, this is the set of it's not polynomials in t. You are allowed to go up to t to the infinity. You are allowed infinite sums in this. That's the difference with polynomials. Unlike zt, because I want to put all of these, all the big and small n's. So they are infinitely many. So I need the ability to take infinite sums. So this is the power series. Essentially, it is viewed as the larger you get to t raised to n, that is a smaller quantity. This is how the convergence can be seen. But we don't need to talk about convergence. You can just define this algebraically, symbolically. It's a set of all these expressions, sigma ai t to the I, where I goes from 1 to infinity, or I goes to 0 to infinity. Yeah, so it's just these formal sums, they are infinite sums. So usually this is what you would want to study. You would want to study the generating function of this count. But this is not the zeta function. So if you know the zeta function already, do you know what is the difference between this and the zeta function? Yeah, that is a that's a property in the end, yes. But can you state it simply at this point? So we will not use this because this kind of is defined via this black box NN. We have no idea about what NN is. So instead of using this, we will use something more compatible with our divisor definition. Yeah, so with this as the goal, we define another power series that's better behaved. Okay, so that is the zeta function. So the zeta function of C of a curve over K is defined as ZT over all the divisors T raised to degree of the divisor. Okay, so this clearly lives in power series over integers. So this is what we will use. Right now it is not clear what is the relationship between the thing which we are interested in computationally, that is the count of points, and this thing which is far more abstract because it took us so much of development to get to divisors. And this is summing over all the positive divisors or non-negative divisors. Summing over all the non-negative divisors. So this is, I mean, one, you can expect a relationship because divisor is nothing but a sum of points, formal sum of points, sigma pi. So, for example, if you have I mean, this possibly can be factored into points. Every divisor is a sum of points and degree is additive. So every monomial here t raised to degree actually can be written as a product of t raised to degree of points. And then the whole zeta function can be factored. So let's do that.
Is this compatible with the definition of NN that you gave in the last slide? You defined that NN consists of those points
Yeah,
such that dp divides n.
yeah,
So now you go back to your function.
yes. What function?
This zeta, the last zeta function,
Yeah,
t to the power dt. So the divisors which will have the degree as a
no, but that was for a point. This is not, I have said nothing about degree of a divisor. Degree of a, if divisor is P1, then it is compatible with that lemma. But if your divisor is P1 plus P2, what is P1 plus P2 to do with P1 or P2? P1 plus P2 is not a point on the curve. I mean, this is other thing. The Jacobian is much bigger than the curve, right? So P1 plus P2 are actually not curve points. They are somewhere else. They are points on the Jacobian. So degree of P1 plus P2, you can't interpret it so easily. But the one good thing about this sum is the following. That it factors into points like this. Do you agree with this formula? So if you just go over all the points, so this is an infinite product, right? So an infinite sum I have now replaced with an infinite product, but now the product is over points, not divisors. And for the, so the proof is simply this: you just observe that this is equal to 1 plus t degree of the point plus t twice degree of the point, and so on till infinity. So it's an infinite product of infinite sums. But you can see that any divisor d which is non-negative appears here uniquely, right? So the two things are the same.
When we multiply these two expressions, then what is t to the power degree of p1 plus degree of p2? These kind of things will be coming. Right?
What do you mean? Degree of?
When we are when we are actually expanding the product.
Yeah.
So suppose you fix a point p1.
Yes.
You will get t to the power degree of p1.
Let's write it down. T to the power degree of p1 times t to the power degree of p2 is equal to t to the power degree of p1 plus p2. That's all. And moreover, t to the power I1 degree of p1 and t to the power I2 degree of p2 is equal to degree of I1 p1 plus I2 p2. That's the divisor form. Okay, so when you look at product of two things in that big product, the monomials actually multiply, and in the exponent you get a degree of a divisor, which is the proof that zeta function factors over the points. Okay, so that's a very nice thing. It's much better looking than your original generating function, and I mean, your hope is that it at least knows about all the points. So in a way, ultimately we'll also be able to count them. Right? Every point is contributing a factor. So
No, I was confused with the degree of divisor notation. The divisor degree is studied that sum of the coefficients.
no. Who said that? What we agreed upon is that degree of a divisor like I1p is equal to I1 times coefficient times the degree of point. It is not I1 plus I2. It is I1 times the degree of the point, which is what is being used. Okay? Because a point is not a point. A point is a cloud of points. You have to count all of them. If the point is an actual point, then you get degree 1. Then you get I1 plus I2. Otherwise, you have to weigh it with the cloud size. So that was defined carefully so that this thing works. Any questions? Yeah, so we have done this not just because it factors, but also because we have now a pretty good understanding up to even Riemann-Roch of the divisor group. And we'll actually use all of that built machinery inside the zeta function. Okay, so for example, what we can, so our ultimate goal is to actually give an expression for the zeta function which is computable. Right now it's an infinite sum, we can't compute it. We also don't know the points, So this all this doesn't seem to help much. But using all the machinery, especially Riemann rock, what we will do is we'll break up this sum into first of all degree 0 divisor, then degree 1 divisor, degree 2 divisor, and within a degree d divisor we'll compute the sum locally and then add everything up. Okay, so this will, I mean, with the kind of methods we have developed, this will be pretty easy now. Although this is, it took people a lot of time to achieve this, but now we have the right tools. So this will, nice things will follow pretty fast. So first observation is that recall that degree does not change up to principal divisors, right? So in any divisor you can add bracket x, degree will not change because degree of bracket x is 0 and degree is additive. So and we have an recall that this exact sequence basically the degree 0 class group is contained in the class group and degree is mapping that to integers. Yeah, so anything you take from degree 0 class group, it will be in the kernel of the degree map. That's all this is saying actually. What we don't know is what is the image of degree. Is it all integers or few integers? We actually know that it's infinitely many integers, right? Do we know that? On the class group, yeah, sure. I mean, you can just take different degree divisors. So you know that actually formally you should be able to show it, but just because this class group is a free sum, there will be, you expect it to be infinitely many integers, but you don't know whether all integers. For example, is there a divisor whose degree is 1? That's not clear. Degree 0 we know because we can take any principal divisor, any function will have degree 0, but is there a divisor whose degree is 1? That is not clear because what may happen is that your curve may have no point at all in the base field. So you cannot just say that I will take P, a point P, because there may not be any point. So you have to go to an extension. But when you go to an extension, say FQ square, there all points have degree 2. So it seems that from 0 you are jumping to 2.
You have to find like the GCD, right? 2 point GCD.
Exactly.
If there are 2 co-prime degrees, then even plus A2 P2 degree, like we go to 1 like that.
Why will GCD help?
So degree of P1 is degree of DP1.
But degree is additive, right? If you take.
Yeah, I can take free from that.
Oh, I see. So yeah. So you have, yeah. So what you have shown is that the image of D, it's an ideal. So it's a principal ideal. So you are going only in multiples of delta. So there is a step function, and just that step function gives you the whole image. So let's write that down. So image of D is actually an ideal of Z, which means that it's a principal ideal. Yes, but you don't know whether delta is 1. So delta may be 2. So you just get even degrees. That's possible because of our base field being arbitrary. So we have to stick with this delta for some time. In the end, we will show that delta is equal to 1. But right now, I don't think it's so easy to show that delta is 1. So with this definition, it already follows you have this exact sequence. Is exact. The only difference from above is that now we have fixed the image delta z. So if you look at the arrow of degree, the image is in the kernel of the last map. So that part is also exact. So there are 3 parts, or 3 parts are exact, which is image of the previous map is equal to kernel of the next map. Right. So this is an exact sequence we'll remember. This is where delta comes from. And now let us, so this last part of the course, we'll just be expanding the function zt. Okay, we'll just expand zt, we will rewrite it, and then we'll keep calculating newer and newer properties of zeta function till we have proved Riemann hypothesis. So in fact, I have not told you what is Riemann hypothesis, so even that will come as we do these expansions. So define CLDC to be the set of divisor classes of degree d, and d is always picked to be multiple of delta because otherwise the CLD will be empty. So we expand with respect to CLD. So we can write, for example, set T as so these were all non-negative divisors. Let's go over the D's that matter, and then let's go over the divisor classes in CLD, and then finally the divisors in that divisor class. Right. So the property of this normal D is what? It's greater than or equal to 0. Its degree is D, and they are all equivalent modulo principal divisors. Right. So we get these 3 sums, and in the end you have degree of D being D. So you get this.
The CLD has all those divisor degree D.
So yeah, we should be careful. So like CL0, it was not the set of divisors, it was the set of equivalence classes, modulo principal divisors. So yeah, because zeta function goes over all the non-negative divisors. So it doesn't care about 2 divisors being equivalent. So it's kind of over counting. And you cannot avoid that because ultimately your goal is to count points and not some equivalence. Right? You want if 2 points look different, they are different. You don't care whether they are equivalent up to principal divisors. So goals are different. So this is a longer expansion. So we do it in 3 parts. Fix the degree, fix the class, go inside the class. So we now study the 2 inner sums. So now you will see some interesting lemmas, but they are, as I said, nothing will be difficult now because of the big development that we have done. So first lemma will tell you the count on the innermost sum. So the number of divisors there which are greater than or equal to 0, this is equal to q to the LD minus 1 divided by q minus 1. Okay, so now the LD sheaf appears magically, right? This probably was the reverse engineering which gave them the LD sheaf. So here zeta function calculation will actually know about the LD sheaf. So why is it appearing? So you already have, remember that the LD sheaf is, again, it doesn't change up to principal divisor addition. At least the dimension will not change. So little l of d is a property of that class. It's not a property of the divisor. So which is why I have written small l of the class, because every element in that class has the same small l dimension. This we had seen before. So how do you prove the count? So fix a divisor in this class. Now, for all d prime in the class, what do you know about d prime minus d? It's equal to some principal divisor. Right? Any d prime you take with the fixed d, the difference is a function, principal divisor of a function, which means that and I should only take greater than or equal to 0, because that's the thing that appears in my count. So for all non-negative divisors d prime in the same class, you have this property, which means that d plus f, or the other way around, f plus d, which is d prime, is greater than or equal to 0. Which means what?
Every d prime corresponds to that.
No, which means that, so immediately this means that f is in LD sheaf. That is the definition of the LD sheaf. So for the fixed d, as you are changing d prime in this greater than or equal to 0 property, these non-negative divisors, they all come from functions from the LD sheaf. We have set up an association. But that would mean that there will be infinitely many D prime because functions are infinitely many. Is that correct? No, that's not correct because now you have to count functions in LD which give you different D primes. Because many functions, for example, if you take a function f and a function 2f, their principal divisors are the same. So you have to count functions whose principal divisors are different. That will give you different D primes. So for f and f prime in LD, the principal divisors are the same if and only if what happens? It has to be a constant multiple. Yeah, so you should not take, you should discount these constant multiples of functions. So what we have shown is that number of D prime number of distinct D primes greater than or equal to 0 in this class is the same as number of non-similar functions in the LD sheaf. Right? Non-similar meaning they have different divisors, which means they are not multiples. So what is that? What's the count? So let's look at the LD sheaf. It has F1 to FLD basis and it's a small k vector space. Right, so it has these basis elements. So how many non-similar functions can you find here?
Is LD are all non-similar?
Oh, I shouldn't have said infinitely many functions. Actually, it's just it's a finite dimensional vector space and the field small k is also finite. So it's actually, this is a finite dimensional vector space, but I need the exact count. The exact count comes out to be this. It just, you take all possible combinations, which is Q to the LD, but then you don't want to take the 0 combination, and you don't want, now you want to discount the multiples. So that's divided by Q minus 1. Fine? That's the expression.
Why was this -1 in the numerator?
Oh, the 0 function. Yeah, and then you divide by q minus 1. So you have some combination, but you discount its multiples. So there are q minus 1 multiples. Okay, so this gives you a good information about the inner sum, right? Now you can actually just simplify the inner sum. It is this number which is the LD sheaf dimension times t raised to d. So now let's move to the second sum. So what is the size of CLD? That's the question. So what we will show is that for all correct degrees, CLD and CL0, what is the relationship between them? You would expect equal, so they are equal. And so it's finite. Okay. Actually, do we know CL0 to be finite? We don't know it to be finite, right? Yeah, that will need a proof. Okay. So this stuff will come from genus, from Riemann rock. Or just from Riemann actually. Yeah, you don't need rock for this. So let's prove the equality. So for a class in CLD and a class in CL0, we have the bijection. We'll just give a bijection from CLDC to CL0C, which will be, where should you send D to? Sorry, DD prime are fixed. Where should you send some arbitrary E to? So just do the obvious thing. Send it to this, right? So degree of this fancy E is D. I mean, it's a class, but you can also think of it as just a representative divisor. So I can talk about degree and everything. So the degree of that divisor is D. On the RHS, it's D plus 0 minus D. So that's 0. And you can clearly see that this is a bijection. Right? You can go both ways, and yeah, it's trivial. So that's the bijection which makes them actually equal in size. That was the easy part. So next is why is it finite? Let's prove that. So because of the previous result, we actually don't need to study CL0. We can take a higher degree and we can study that. So let's do that. So consider D in delta Z such that D is quite large, greater than or equal to G. So for bigger degrees, we have nicer properties. So we are hoping that CLD will be able to understand. So let D be a divisor in a class which is in CLD. So by Riemann's theorem already you get that L of this L minus D difference is at least, it is lower bounded by 1 minus G, which for high degree is 1, yeah. Right, that's a good thing. So there is some function in the LD sheaf. So this means that there exists a non-negative divisor in D. Right, because LD there is a function, you pick that function f, add it to D, then you get greater than or equal to 0. So D plus f is greater than or equal to 0 and D plus f is in this class, is in the same class. So you have found a non-negative divisor in this. So which means that CLDC is less than or equal to the number of non-equivalent non-negative divisors. Of degree D, right? Because as you change this fancy D in CLD, every time you will find a positive non-negative divisor present, and they are all degree D. So you just have to count how many degree D non-negative, non-equivalent divisors are there. So say point P appears in such a divisor. Okay, non-negative divisor of in CLD. Suppose P is a point there. So the degree of the point will be less than or equal to degree of the divisor where it is contained, which is D. Yeah, so just think about what we are doing. You have these non-negative divisors, they are all non-equivalent. So you look at the support, so you see these points. Whatever point you see, P, its degree is bounded by D. So you have to ask the question, how many points are there of a degree D, bounded by degree D? That's finite. So since number of such points is finite, what you have learnt is CLDC is finite. Is that enough? It's finite, but there is also this coefficient which appears, right? A point may appear many times. Yeah, that is also being used, correct. That's true. Let's write that. Yeah, so both, so the number of points is finite and their multiplicities or their orders are also finite. So overall you get finite combinations. Yes, that's good. And there was no negative order. So this is this is a finite set. Okay, so that I think is good for today. Uh, so you can just now next time we will. So we have computed the innermost sum and the middle sum also now just depends on CL0. So CL0 is the class group size. So you will get now an expression in terms of, so two fundamental things are appearing here in the zeta function already. It's just sum of multiples of delta, where the sum is just dependent on the LD sheaf and the class group size. Okay, it will be a simple expression, and then we will study its famous properties.